Now we get to the fun one, soft EM. And it's sometimes called the Baum-Wells re-estimation, and it's an instance of the forward-backward algorithm, okay, for probabilistic graphical models. And you will see why it's called forward-backward in a second. But the answer is you use the forward algorithm and the backward algorithm together. You use the alphas and the betas in order to do the soft assignments. Okay, so I think of this as the Gaussian mixture models for hidden Markov models. I put it in quotes because it's not entirely true, but it helps to get an intuition. You've done Gaussian mixture models, but the basic intuition is that, okay, I've got some data, and they're spread out like so, okay? And I want to model that with more than one Gaussian. And each of those Gaussians will have a mean, but also some covariance matrix associated with that mean. Okay. Now what happens when I have to decide which one of these components does this observation belong to? In k-means, what would I do? I would just find the closest mean and just make a hard assignment saying this point belongs to this point, and it doesn't know anything about this mean. Ignore it. But with a Gaussian mixture model, that's not actually what you do. With a Gaussian mixture model, you say, listen, this point might be closer to this mean, but it's also like almost close to this point. So I take that soft assignment of this point to these two components into account. Okay, and that's what happens with soft EM as well. Does that make sense? We're not going to say that this specific observation x1 belongs to this state and only this state. We're going to say that this observation belongs to this state with a probability of 0.5 or 0.6, okay, instead of counting things up in a hard way. To do this, we're going to define this new probability of being in state J at time step t. This probability is denoted as the little gammas, okay? So this is the probability of being in the state, and let's make it now, given that I've observed everything else that happened. Okay? And this is a probability. It's going to be between 0 and 1. Okay? Now, to calculate these gammas, we're actually going to end up using our alphas and our betas. Okay? And these gammas are going to serve as our soft counts of being in a particular state. A soft count of being in a verb or a noun. You can write it out like this. Where the fudge does this come from? Base rule, that's exactly right. P of A given B is P of A, B divided by P of B. Okay, cool. Go and look it up on Wikipedia if you can't remember. Okay, and then what I'm going to do is I'm going to split off my sequence here, my x1 to t. I'm going to split it up into two parts. The one part is from 1 to little t, the time step that I'm currently in, and the second part is from t plus 1 up to the end. Okay, this is exactly the same as that. Okay, wonderful. And now I can write this out. I can expand this a little bit. I use the chain rule of probability theory. So this is like A, and then the remaining stuff is like B, and the B goes there. And then we divide this thing by 1 to capital T. This is just alpha. This, go back, is just the beta. So you end up taking the alpha and the beta and dividing by that. Where do I get this? Oh, where do I get this? Okay, wait, so I can tell you where I get the alphas. I run the forward algorithm. Where do I get the betas? I run the backward algorithm. Where do I get this? What is this? This is the marginal probability of the sequence, according to my current hidden Markov model. Okay, so this is just problem 1. That's just problem 1. So you can use either the forward probabilities or the backward probabilities in order to solve that one. This is the one definition that we need, okay, to figure out these soft counts of being in a particular state at a particular time step. The other types of counts we need are soft counts for transitioning between two states. And for these, you define this symbol. Can someone tell me what this symbol is? Anyway, it's very clear. I do not know what that symbol is, so let's just call it John. Okay, so you need to basically figure out John for going from I to J. And again, this is going to be a soft probability between 0 and 1, telling me what is the probability of transitioning from a verb to a noun at a particular time step, t. So these are going to be soft counts. Okay, so instead of saying, oh, in Viterbi I went from a verb to a noun, so I get a count of 1. What's going to happen now is I'm going to go from a verb to a noun with a count of 0.3 or something like that. Okay, and this is what these Johns are capturing. I don't want to bore you because the steps are basically the same. Again, you use Bayes' rule, you end up with this. You split up these observations into a whole bunch of small little parts, and then go and sit in the bath with some red wine, figure this out for yourself. You can see that you can split it up in terms of alphas, transition probabilities, your emission distribution, and then your betas. And you all chain them all together, and that gives you your Johns. I'm going to run through this so that we can get to the example where things are actually going to make sense. But in the soft EM algorithm, in the E step, in the expectation step, we are basically going to figure out the probability of being in a particular state at a particular time point. Okay, so it's not going to be like Viterbi, where we just get a 0 or a 1 for being in a particular state at a particular time point. We're going to get soft counts. Okay, so what we do is we run the forward and the backward algorithms. We get our alphas and we get our betas using the current estimate of the model parameters. Okay, so we started out at some point and we've got our current parameters. We run forward, backward, get alphas, get betas. Now, if we've got the alphas and the betas, then we can calculate these gammas and we can calculate the Johns. Okay, and the nice thing is, then you can start to sum things up. Okay. So just stare at that for a second. Can you see that what I'm doing is I'm running over my entire sequence and I'm counting up, soft counting up, how many times am I transitioning out of state J? Okay, so I'm counting up in a soft way, how many times am I transitioning out of a verb? If I sum up all the gammas over all time for the state verb, then I'm getting a soft count for how often do I pop out a verb. Similarly, if I sum up all my Johns from I to J over all time, then I get something like a soft count for going from a verb to a noun. That's in the expectation step. So I run forward, backward, and I get these things. In my maximization step, I'm going to do basically maximum likelihood estimate, but instead of hard assignments for whether I'm in a particular state or transitioning between states, I'm going to take these soft counts into account. So for instance, well, this is the equation for the transition probabilities. So let's say I want to know the transition probability of going from a verb to a noun. Then what I do is I take my soft counts from verb to noun and I divide that by the soft counts of going from verb. And what is this? That's my gammas. What is this? Those are my Johns. The equation looks exactly the same as with the hard EM algorithm. The hard EM algorithm just didn't have the word soft there, but now we have these soft counts. Okay, so for the emission distributions, if it is a categorical distribution, like the parts of speech example that we've looked at, then if I'm in the verb class, the probability of seeing water is the expected times I am in the verb state and I see water. I'm going to divide by the expected times I, what should I write next? Verb state. And these things are the soft counts of being in the verb state. Okay, and then this, you just need to mathematically go and look a little bit here. But here you've got the soft counts of the verb state. And here I've got an indicator function which counts up how many times that I observe water while I was in the verb state. Okay, so here I've got a little indicator that's a 0 or a 1. If my current observation, if the output, the emission at the current time step is equal to water, then I add the soft count. If it's not water, then I don't add the soft count for being in the verb state. Okay, and I'm adding up all of those. And then you end up with this soft equation here. Okay, and that's the maximization step. Okay, so you now know the expectation step, the maximization step. You need all the different parts that we've solved up to this point in order to do this. But if you've done the alphas, you've done your betas, you can calculate your gammas, you can calculate your johns, and then you end up with these equations. I'm going to do an example. Hang on to your seat. We're going to train a hidden Markov model with a pen and a paper. Okay, that's pretty exciting. So our example is this running example where I've got a hidden Markov model with 4 states. State 0 is the start state, state 3 is the end state, and then I've got state 1, which I've labeled as consonant. It's a consonant-ish state, right? So in real hidden Markov model land, you won't have a C here. You will just have 1 and you will just have a 2. But I like to think of them as consonants, and state 2, I like to think of them as vowels. Okay, is everyone with me? The output vocabulary, the type of things that this thing can generate is it can generate M's, it can generate O's, and it can generate H's. Okay, so this might model a small child that has learned these 3 sounds. Okay, and now this HMM can generate things like more, or, things like that. Okay, for some weird reason. Okay, I give you a single training sequence. The single training sequence looks like this. Okay, that is your training data. Okay, and because we're learning the model, we want to estimate its parameters. There are 2 sets of parameters. The one is the transition probabilities. So for instance, I want to know what is the probability of transitioning from a start state to my C state. What is that? Okay, that's one example. But I want to know all of the transition probabilities, all of them. Okay, cool. And then the other probabilities that we need is the emission probabilities. So for instance, I want to know what is the probability of when I'm in a C state generating an M, okay? Or what is the probability of when I'm in the V state generating an H? Okay, and we want to estimate that, we want to estimate that, we want to estimate that, okay? We want, for the emissions, we need to estimate this phi C for M, O, and H, and we need to estimate a phi V for M, O, and H. Okay, sometimes you can think of the phi as a vector, and there's a phi C vector, which has those 3, and then there's a phi V vector, which are M, O, H for the V state. And that's what we want to estimate. This is our training sequence. Cool, let's run the algorithm. SoftEM is a little bit tricky, okay? So, but we're going to do it nonetheless. The E stands for expectation, and we're in the E step. What do we do? What's the name of the algorithms that we're going to have to run here? So we run the forward-backward algorithm, and actually the forward-backward algorithm is going to give us a ton of stuff. It's all these soft counts that we need. We know we're going to start in the start state. We know we're going to end in the end state, okay? So that's easy. Remember, forward-backward gives us soft counts of being in particular states at particular points in time. We're going to calculate basically these gammas and these johns. Let's go with the gammas. So just very quickly, let's just remind ourselves of what the fudge is a gamma. The gamma is the probability in that particular time step of being in a particular state. Okay, so there are 4 states in this HMM: start state, end state, C, and V. Okay, at time step 0, let's write all of them out. And we're at time step 0. Okay, what's the probability of being in start state at time step 0? 1. More obvious, right? Okay, and that implies that the others needs to be 0. And that's exactly correct. This was time step 0. Now we're at time step 1. Okay, now there's a bunch of options. We're not going to be in the start state, and we're not going to be in the end state. Okay, so those probabilities are 0. That's easy at least. Now we need to figure out what is the probability in start step 1 of being in C. And to do that, we need the alphas and the betas, and we normalize them properly. We get the alphas and the betas, and normalize them properly by running a forward-backward algorithm using my current estimates of the parameters. So you run that, you code that up in Python, you run the algorithm, and you end up with a number. Okay, I'm going to make something up here. So let's say it's 0.9 of being in the C state at time step 1. Let's say the probability of being in the V state at time step 1 is 0.1. I'm just making stuff up here. Okay. We go on like this. So we calculate the gamma for C at time step 2, and I'm just going to make this 0.7. Time step 2, V, oh, that should be 0.3. We run the forward algorithm like this, okay, and we calculate all these gammas for all these time steps. I'm just going to make up some gammas for us over the time steps, and I'm just going to focus on the C class for now, the C state. And then at time step 1, 2, 3, we've got 0.3, 0.8, 0.1. Doesn't matter that much. These are just made up things. These are the gammas, okay? We still need our Johns. Should probably call it by its proper name, but now it's too late. The Johns are basically these soft counts. I'm just going to focus on one of these, okay? And that is the transition from a consonant to a vowel, okay? So what I need to do is I need to run forward, backward, plug in the equations, the alphas and the betas, the transition probabilities and the emission probabilities. That's all involved in the gamma. And I get a value. At time step 1, I get a value that's, I don't know, 0.2. And that's that time step, going from there to there. The next one, and from consonant to vowel, let's just say that is 0.3. And we calculate them for every pair of states, and for all the different type steps, you calculate these values, okay? So let's just make that up, 0.2. You've calculated your alphas, your betas, and then you calculated these other variables as well, okay? Now, what do we do in the M step? We do maximum likelihood estimation. And now, instead of using absolute counts, we use these soft counts, okay? So for instance, if I ask you, what is my maximum likelihood estimate of going from C to V, then you could say, well, this is the soft count of going from, and I'll ask you what that is, and divide it by the soft count, and I will ask you what that is. At the top here, soft count, this one is easy, it should be CV. Okay, and then I divide there by the soft count of exiting what state? C, that's right. Tell me, what is this soft count CV here? How do I calculate that? So you're going to add up the soft count of going from a C to V. So you're going to have to add up what? You're going to add up these things. Okay, so literally what you have there in the numerator is 0.2 plus 0.3 plus 0.2 plus 0.9 plus blah, 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 blah. Okay, you add up all these numbers. Now, what do you divide by? The soft count of C. Okay, so tell me the values there. It's 0 plus 0.9 plus 0.7 plus 0.3 plus 0.8 plus dunk, 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 dunk. Okay, you're adding up all the numbers in that gamma 0. Okay, because this is the number of times that I've exited the C state. Okay, these are the number of times, and when I say number of times, I mean the soft number of times that I went from a C to a V, and you add all of them up. Okay, does that make sense? And okay, the equation here, if you want to scribble it down, this is really the summation from T0 up to capital T of these things, which we've been calling John for some weird reason, okay, divided by the sum from T0 up to capital T of these gammas. Okay, in a very similar way, you can estimate the emission probabilities. Does this make sense? I mean, it's a little bit weird. You have to get used to this idea of soft counting, but that's what happens on the inside of these algorithms. So we've got these three problems. We figured out the marginal probabilities, we figured out the most likely states, and then the problem of learning we've solved using the forward-backward algorithm, which is heavily involved in there, but really it's called the expectation maximization algorithm. And we looked at 2 flavors, the hard one, the Viterbi one, or the soft one, Baum-Welsh. And we looked at both of those.